Okay, I had started with the matrix method of structural analysis. Okay, so once concept what I introduced was about the stiffness and flexibility with respect to a spring over there. Okay, so that is the property of the member what we saw, a stiffness or the flexibility here. So with the help of this property, that is the stiffness or the flexibility, we can go for analyzing a structure over here. So there will be two methods. One will be force based and the other displacement based. Okay. Don't put anything in the chat box now. If you have any doubts, raise your hand or unmute and speak. Attendance will be considered in the end. I'll tell you. So the two methods are the force based method and the displacement based method. So flexibility method is a force based method. Okay. Whereas the stiffness method is the displacement based method. Okay, what I mean by force based method and displacement based method is in flexibility, the forces, redundant forces will be taken as unknowns. Whereas in stiffness, the displacements, unknown displacements, okay, so the unknowns will be displacements, what you will be determining. So that's why we call this as a displacement based method over here, okay, and the flexibility method as a force based methods, okay. So you'll be determining these unknowns first. Now we'll begin with the stiffness method, okay. What we had last week in the class was we saw what is the stiffness and flexibility by considering one simple spring. Okay, for this only one displacement was possible in one direction. Okay, so this was the displacement which was possible in this spring. So it was having 1 degree of freedom. So with respect to this displacement, we have defined what is the stiffness. So stiffness is nothing but the load required to produce unit displacement in this spring or in this member. Okay, so K can be expressed as force divided by the displacement, force per unit displacement. That is the definition or what is meant by the stiffness. Okay, so the chat is already cleared. I don't have any of the attendance right now, so you will be only able to give the attendance at the end. uh, so what I have is this. Okay, similarly I can go for telling or expressing the flexibility. Flexibility is the displacement under unit force. Okay, so I can take it as displacement, okay, under unit force delta upon p. These are inverse of each other, flexibility and stiffness, they are inverse of each other. That is what we can conclude. Now this was with respect to 1 degree of freedom. There was only one displacement which was possible and we had taken a coordinate in the direction of displacement. Okay, so with reference to the coordinate we are expressing the stiffness or the flexibility. Okay, whatever you displacement you give, it will be in the direction of this coordinate, or whatever force you apply will be in the direction of the coordinate when you are finding the stiffness or the flexibility over here. Okay, so when it is question of multiple degrees of freedom, if say in our structure we come across multiple degree of freedom, there will not be just 1 degree of freedom. There will be rotations, there will be sway, or the translations which will be existing in the structure. So there will be more than 1 degrees of freedom. So in that case, what we have is the matrix. Okay, this matrix will come in picture. So we can express the same relation in the form of a matrix over here. What this P is equal to K into delta can be put in the form of matrix when we have multiple degrees of freedom, when we are working with multiple degrees of freedom over here. So that is called the matrix formulation, okay, or formulation of stiffness and flexibility matrix. So here also the same thing, that is P is equal to K into delta. From our basic relationship, I have taken this. So it has been put in the form of matrix over here. Now, how you obtain this stiffness matrix, we'll see that. Okay, this is an unknown matrix. When we are working in the stiffness method, this delta or the displacement matrix is not known to us. This will be unknown. Okay, in case of stiffness method, and this is the force matrix. Okay, P matrix will be called the force matrix. We'll see how we obtain these matrices. Okay, but the stiffness matrix. To obtain the stiffness matrix, what you have to do is you'll have to consider the coordinates what we are assigned. Okay, and then we will be able to develop this stiffness matrix. Some properties of this stiffness matrix are it is symmetric matrix and it is a square matrix. The order of this matrix depends on the degree of freedom. If there are n degrees of freedom, the size of matrix will be n by n. Okay, so that will be the size of matrix. Similarly, the size of this matrix, these are column matrix, the force matrix and the displacement matrix are the column matrix. 18CV59, any doubt over there? You raise the hand. 18CV59, you can unmute and ask the doubt. So these are the three matrices what we'll be dealing with: force matrix, stiffness matrix, and the displacement matrix will come in picture. Okay. Now let us move ahead with the stiffness method. Okay, and see how we are going to analyze the beams, frames, or the trusses with the help of stiffness matrix. Okay. So first thing what we are going to do here is to determine what is the degree of freedom. Okay. So here determine the degree of kinematic indeterminacy or the degree of freedom. Okay, that has to be determined. Okay, I'll take an example later, but right now, what is the procedure? How we are going to do it? Okay, that we shall see over here. And once you identify what is the degree of freedom or the degree of kinematic indeterminacy, what we are going to do is we are going to assign the coordinates. Okay, so we have to assign coordinates at the points where independent displacements exist. Okay, so where these independent displacement exist, they are normally come at joints or at the supports. Okay, these are the locations where we have independent displacements. Like you had rotations at the joints. Okay, in the frame there were rotations taking place at the joint. Okay, or there were translations sway which were considered at the joints. So these coordinates or the independent displacement will exist at the joints or at the supports. Okay, so these are normally at joints or the supports, or maybe at both the points also. So you are going to assign the coordinates. If there are n degrees of freedom, then you will end up with n coordinates. It depends on what is the degree of kinematic indeterminacy or the degree of freedom of the structure over here. Okay, I'll give you the points. What are these points later? But right now you understand what is the procedure over here. Okay, so corresponding to n degrees of freedom, you'll come across n number of coordinates. So these may be coordinates which are assigned to rotations, or maybe the coordinates which are assigned to translation also. Okay, there may be both of them. The displacement doesn't just mean rotation. It means there may be translation delta, like sway is one of the translational displacement. Okay, so like that we are going to assign the coordinates over here. So after assigning the coordinates, once I assign the coordinates, next what I'm going to do is I'll be restraining that structure. So what you have to do is you have to restrain the displacement at the coordinates. Wherever the displacements were existing, what we'll do now is we'll lock those displacements, we'll make them zero, we'll restrain them. It is just like you find the fixed end moments. Okay, when you are finding the fixed end moments, all the end conditions, what you are doing is you are considering them to be fixed. So the same thing will be done here. We will restrain all the displacement, we'll make them zero and go for determining the forces which will develop in the coordinates. Okay, so in the third step, what you will do is restrain the displacement at the coordinates and determine the forces Okay, so after restraining the structure, I'll go for finding the forces which are developed in each of the coordinates. Okay, let us say this is our P dash. We have P dash number of forces. So P1 dash is the force in the first coordinate, P2 dash is the force in the second coordinate, and P3 dash is the force in the third coordinate, and so on up to Pn dash. If there are n coordinates corresponding to n degrees of freedom, we'll get n number of forces in the coordinates. What are these P1 dash, P2 dash, P3 dash? They are the forces which are developed when we restrain all the displacements in the coordinate. Okay, so these are the forces, set of forces which are developing in the restrained structure at the coordinates 1, 2, 3, 4 up to n. They represent the number of coordinates. Okay, here immediately once you identify the degree of freedom, you can write what are the displacement, unknown displacement, delta 1, okay, delta 2, delta 3, so on. I can write this matrix immediately. These are all unknowns to me. So up to delta n. Okay, so these are the displacements. Now you are restraining these displacements. You are making them zero. You are considering the end conditions to be restrained over there. After doing that, what forces are developed in the coordinates? Okay, if I determine them, these are those forces P1 dash, P2 dash up to Pn dash. Okay, now this is what we have up to here. Now after doing this, now what I am going to do is I'll be finding what is the force required for developing the displacements delta 1, delta 2 up to delta n. Okay, say for example, this is one of the member. Okay, so you want to find what are the displacement that are there at the ends or at the supports here. So there'll be two rotations, theta A, theta B. Okay. So what you do is I have identified the degree of kinematic indeterminance here. dk is coming out to be 2. That is theta A and theta B. Okay. Rotation at A, rotation at B. So my unknown displacements are theta A and theta B in this case. Okay, so this becomes my displacement matrix delta. Okay, this is my displacement matrix delta. This is what I'll be doing in the first step. Next, what I'll do is say there is some loading present on this member. Okay, so let us not worry about the values or the calculation over here. So what I'll do next is I'll consider these ends to be fixed. Okay, so I'll make these restraints, apply these restraints. I'll consider these ends to be fixed. I'll make all the displacements zero here. Okay, first is I identified what are the displacements, unknown displacement. Next, I'm going to make them zero. I'm considering that ends are restrained. With this condition, what I'll do is I'll find out this P dash matrix, which is the force matrix, one of the force matrix over here. Okay, so it consists of P1 dash, okay, and P2 dash. It may be WAB square by L square, WA square B by L square. We have the formula for determining what is P1 dash and P2 dash. Okay, now what we will do next is we'll allow the displacement to take place here. Okay, in this restrained structure. So if I want to have a rotation of theta A at end A, okay, what I have to do, I have to apply some force over here to rotate this member about end A by theta A. I have to apply some force. What is that force? Required force here. So that can be determined by our stiffness coefficient. Okay, so what is the stiffness coefficient? The stiffness coefficient is the force required for unit displacement. This is the force required for unit displacement when delta is 1 or theta A is 1. What is the force required? That I know. If I want to produce a displacement of theta A, what I have to do is I have to simply multiply this with theta A. Okay, I have to multiply the stiffness coefficient with the required displacement. That is what I have to do here. Okay, so for doing this, what I require here is the stiffness matrix. Okay, stiffness matrix is required. So here what we'll do is we'll come up with the stiffness matrix. The next matrix what I need is the stiffness matrix. Now, how do I develop that stiffness matrix? For that, what we have to do is we have to consider each of these coordinates one by one. Okay, so let me take out all these loads. I'll not take any applied loads over here. Okay, then what I have to do is, by definition, stiffness is force per unit displacement. Okay, force per unit displacement. So in this procedure, what you will do is, you will apply a unit displacement in the first coordinate. Okay, theta a and theta b, where my unknown displacements. So my first coordinate is at a, and my second coordinate is at b over here. Okay, these are my two coordinates corresponding to two unknown displacements. Rotation at a, rotation at b are the two unknown displacements. At those points, I have assigned two coordinates in clockwise direction. Okay, so for developing the stiffness matrix, I will take the first coordinate over here. Okay, so what I'll do is, I'll apply unit displacement in the first coordinate. I'll give a unit displacement in the first coordinate and no displacement in any other coordinate. Okay, so this is 1 unit, 1 radians, 1 degree, whatever it is. So I'll apply unit displacement, and now if I find out what is the force required for this unit displacement, okay, if I now find out what is the force required to produce unit displacement in this first coordinate, okay, that will be my coefficient of stiffness, or the stiffness coefficient. Okay, K was expressed as force per unit displacement. Okay, so here what I am doing is, I am giving unit displacement, and whatever is the force required for this unit displacement, if I find out that, that itself will be the stiffness coefficient. When delta I will become 1, K will be equal to P. The stiffness coefficient will be equal to P. Now at this point, what I am doing is, I am considering the first coordinate. Okay, so what I will be able to find out is, what is my K11, force in first coordinate due to unit displacement in first coordinate. This is one of my stiffness coefficient. I applied unit displacement in the first coordinate, and I am determining what is the force required for this unit displacement. So that will represent the stiffness coefficient K11, force in first coordinate due to unit displacement in first coordinate, K11. Okay, now at the same time, keeping unit displacement in the first coordinate, if I go for finding out what is the force in the second coordinate, okay, the unit displacement is applied over here in the first coordinate. Okay, I'm not allowing any displacement in second coordinate, it is still fixed. Okay, so this is still fixed over here. Okay, so having applied unit displacement in first coordinate, if I determine what is the force in second coordinate, that will represent the other stiffness coefficient K12, force in second coordinate due to unit displacement in first coordinate. Okay, so by this I got to know two stiffness coefficients in the stiffness matrix, K11 and K12. K11 and K12. If anybody is having doubt, please unmute and ask me. I'm telling about how to develop the stiffness matrix. I'm not using any formula. Okay, so let us just see what procedure will be adopted for developing the stiffness matrix. Later, we have the formula for determining what is this, what are these all coefficients. Okay, we'll apply the proper formula and find out the values over there. So up to this point, one is, in the given structure, we identified the degree of kinematic indeterminacy, or the degree of freedom over here. Okay, that is the first step. You have to find out what is this degree of kinematic indeterminacy. Okay, and identify the independent displacements. Once I know what is my degree of kinematic indeterminacy, I will be knowing what are the independent displacements there. Okay, so I have, say, n number of degree of freedom. So there will be n number of displacement that will be taking place at those points. Okay, then what I'll do is, I'll assign coordinates. I'll assign the coordinates at these locations. Wherever the displacements are taking place, at those locations, I'm going to assign the coordinates. They are just directions, reference directions. They are the coordinates are nothing but reference directions. Like you have X coordinate, Y coordinate, like that you'll be here you'll be having some references. Okay, some coordinates what will be assigned by us. Okay, so these coordinates will be numbered 1 to n, depending on what is our degree of kinematic indeterminacy. If the degree of kinematic indeterminacy is 3, we'll be having 3 coordinates. If it is 2, we'll be having 2 coordinates. Okay, and accordingly, we'll have either 3 displacements or 2 displacements, depending on what is our degree of kinematic indeterminacy. Okay, is that clear? The first 2 step, what we did is kinematic indeterminacy is identified and the coordinates are assigned. Immediately I can write what are my unknown displacements in these 2 steps. Okay, I'll be able to write the displacement matrix. One matrix we wrote here. What is my displacement matrix? Say in this beam, theta A and theta B. Displacement matrix consists of 2 elements, theta A and theta B, which are the unknown displacements. So like this, I'll be able to write this displacement matrix here. Okay, so once I'm done with this, I have assigned the coordinates. Okay, I identified the unknown displacements. Okay, then what I'll do is I will restrain the structure. Okay, I'll go for finding the fixed end moments, just like fixed end moments. We are actually finding the fixed end moments only. Here the terminology used is slightly different. So I'll restrain the structure, and what I'll do is I'll find what are the forces developed in each of the coordinates. Okay, I'll lock all this displacement. I'll make them 0. I'll not allow any displacement in any of the coordinate. I'll just make the joints fixed. Okay, and find what forces are developed in the coordinate due to the applied loads. Okay, so they represent this force matrix P1 dash, P2 dash, P3 dash up to Pn dash. Okay, so this is my one of the force matrix what I have, P dash. P dash matrix consists of the forces which are developed in the coordinate, okay, due to the restraints over there. Okay, in the restraint structure, whatever the forces are developed in the coordinates will be placed in this P dash matrix. Okay, so after this, the next thing is I want to develop the stiffness matrix now. So how I do that? I'll take the structure, whatever it is, beam or frame, okay, and then what I'll do is I'll just take the first coordinate in that. So in this, what we'll do is we'll consider each of the coordinate at a time and give unit displacement in that coordinate and determine what is the force required for that unit displacement. So let us say in this case, if I take that beam, there were 2 coordinates. Coordinate 1 was at A and coordinate 2 was at B. So at B, I'll keep it restrained. I don't want any displacement to be given at B. And what I'll do at A, I'll give unit rotation because there was a rotation which was considered to be unknown displacement in this case. Okay, so here what I'll do is I'll produce unit rotation at joint A, 1 unit rotation here. Now, when I give 1 unit rotation at joint A, what is the force required for giving this unit rotation? If I determine that force, that will represent K11, one of the stiffness coefficient, okay, or one of the elements of the stiffness matrix will be K11. Force in the first coordinate when unit displacement is given in first coordinate. That is what this means, okay. So K11, what it means when you give unit displacement in the first coordinate, what is the force required here? Okay, if I find out that force, that is the K11. Okay, so when you are giving the unit rotation in first coordinate, you'll also find that there is a force developed in other coordinates also. For example, in this case, in the second coordinate, there'll be a force developed here. So if I find what is the force in second coordinate, when unit displacement is given in first coordinate, what is the force developed in second coordinate? If that is determined, it will give us one more element of the stiffness matrix, K12. Okay, K12 is force in second coordinate due to unit displacement in first coordinate. Force in second coordinate due to unit displacement in first coordinate. Okay, so this is what I did first. Okay, next what I'll do is I'll move to the next coordinate. I'll go to the second coordinate. Now what I'll do is I'll give unit displacement in second coordinate only. Okay, after finishing with the first coordinate, we'll move on to the second coordinate. And what I'll do is I'll give unit displacement in second coordinate. And please note, I'm giving displacement in the direction of the coordinate. If I have taken the direction of coordinate as clockwise, here I'll be giving unit displacement in the direction of the coordinate only. So here what I did was I have given unit rotation in the second coordinate now. Okay. So what is the force required for unit rotation in second coordinate? If I find that, it is going to give me one more element of the stiffness matrix. Okay, K22. K22 is the force required in second coordinate for unit displacement in second coordinate. For giving unit displacement in the second coordinate, what is this force? Okay, what force you have to apply in the second coordinate? If you find that, it is K22. Okay, so that is one more element of the stiffness matrix. Now, when you are given the unit displacement in second coordinate, when I given the unit displacement in second coordinate, at that time, if you are able to find what is the force in first coordinate, okay, force in first coordinate, if you find that, it will be K21. Okay, it will give me one more element. What is this K21 representing? Force in first coordinate due to unit displacement given in second coordinate. Okay, so this will be our stiffness matrix. This will complete our stiffness matrix. If you find all these elements, it will give you the stiffness matrix. Note that K12 and K21 will be same because property of stiffness matrix is it is symmetric. It is symmetric about the principal diagonal. So K12 and K21 will be same. If I find K12 initially, it is not required to find for me to find K21. It will be same always. So these are our elements of the stiffness matrix. How I find them? By giving unit displacement in each of the coordinates and calculating forces in all the coordinates. I'll take first coordinate, give unit displacement in first coordinate, and find out what are the forces in first and second coordinate. So that will tell me K11 and K12. Then what I'll do, I'll take second coordinate, which was at point B. Okay, I'll apply unit displacement in the second coordinate. Okay, what is the force required for unit displacement in second coordinate? If you find that, it is K22, this element of the stiffness matrix. Similarly, if you find what is the force developed in the first coordinate because of unit displacement in second coordinate, that will be K21. Force in first coordinate due to unit displacement in second coordinate. Okay, K21. Now we'll relate this with the basic equation. Now these are the forces due to unit displacement. If I want to know due to theta A and theta B, what are the forces developed in the coordinates, then what I'll do is I'll simply multiply this, okay, this matrix with the theta A and theta B. If I multiply this matrix with the displacement matrix theta A, theta B, it is going to tell me what is the force due to the displacements which are given in the at joint A and B. At joint A and B, actually there were displacements theta A and theta B. Okay, so due to these displacements, for theta A to develop in first coordinate or at A, and theta B rotation, theta B to develop at B, what is the force required? I have to just multiply this stiffness matrix with the displacement. Okay, so this is P delta. Now we are going to apply the condition of equilibrium. Okay, at A, when you add up all the forces, it should come out to zero. Okay, so or it should come out to whatever the external force is applied over here. So net force at A will be sum of this P dash and this P delta. Okay, so I can write the equilibrium condition as P, the net force in any coordinate will be equal to P delta, the forces due to the displacements at the coordinate, plus the forces due to the applied loads, that is P dash. Due to applied loads, we are determined by restraining the structure. So net force in any coordinate will be equal to forces due to the displacement at that coordinate plus the forces due to the applied loads on the member. Okay, this is our equilibrium equation. This is what the equilibrium equation says. Okay, now further I can substitute for this. I'll come to this later. For these matrices, okay, the displacement matrix, force matrix, what I discussed just now, you can clear your doubts if you have any doubts regarding the force matrix, displacement matrix, or the stiffness matrix. So what I said was the net force in any coordinate can be expressed as the forces due to the displacement in the coordinate plus the forces due to the loads applied on the member P delta plus PL. Further, what I can write? I can write it like this. What is this? P delta was equal to K11, K12, K21, and K22. I am substituting for this P delta multiplied by theta A, theta B over here. Okay, displacement matrix plus what was this PL in our case? Just in the example what I took, it was equal to P1 dash and P2 dash. Okay, so this is our P1 force in the net force in the first coordinate and net force in the second coordinate, P1 and P2. Okay, now what I'm interested in is finding what is this theta and theta B. Okay, so looking at the joint, I'll be able to tell whether there is any force, externally applied force on that joint or no. P1 and P2 are the forces which are directly applied in the coordinate, directly applied at the joint or at the support. Okay, maybe there is a couple which is applied at the support or at the joint. Okay, or there may be a direct load which is applied at the joint, a concentrated force may be applied at the joint. So all these values will come in this matrix, this P matrix, which is another force matrix here. Okay, so I'll be knowing this P1 or this P matrix is known to us. PL matrix we have determined by restraining the structure. The stiffness matrix, we have developed that by giving unit displacement in the coordinates. Only thing that is unknown to us is this displacement matrix, delta matrix. So I can go for finding these unknown displacement by rearranging these matrices, theta A and theta B. Okay, so I can put it as what? It will be equal to this K inverse, okay, so K inverse into this P, that is P1 and P2, okay, minus P dash, P1 dash and P2 dash. So I can rearrange these terms and go for finding what is my theta A and theta B, the displacements. Once I know these displacements, determining the bending moments or the other forces can be done. Okay, so this is what we have in this stiffness matrix or stiffness method here. Okay, we require the force matrices to be written over here. We have to develop this stiffness matrix K for the given structure. We have to identify what is our displacement matrix or what are the elements of the displacement matrix, plus what are the forces due to the applied loads have to be determined in the form of P dash. Okay, sorry, this is P dash, not PL. I have called it as P dash. Okay, so this is my P dash matrix. So this is what the basic steps which are involved in this stiffness method. Okay, only thing is this you can readily identify what are your unknown displacements. You'll be getting that just by looking at the structure, identifying degree of freedom or degree of kinematic indeterminacy. I'll be able to tell what are my unknown displacements. Okay, theta A, theta B, these can be identified over there. Now question is about P dash. P dash matrix will be obtained by restraining the structure. Okay, you have to restrain the structure, find the fixed end moments, so they will be arranged in this P dash matrix. Okay, then what is there is the main thing is for developing the stiffness matrix in this case. So stiffness matrix, how you are going to develop that is by considering each of the coordinates. Okay, I'll take the first coordinate, apply unit displacement in first coordinate, determine what is the force required in the first coordinate. Okay, just a minute. Please tell me if you have any doubt. I'll come back. Hello, sir. Hello. ಇಲ್ರಿ ಸರ್ ಅದ ಮತ್ತೆ ಇಲ್ರಿ ಸರ್ ಅಂದ್ರ ನಾನ್ yes, okay. I want you to tell me any doubts if you have when you are developing the stiffness matrix. Okay. So if this was a case, what I considered for 2 degree of freedom. If there is 3 degree of freedom, what you'll do is you'll be having 3 by 3 stiffness matrix. So you'll take the first coordinate and give unit displacement in first coordinate without giving displacement in any of the coordinate. Okay, we will not be giving any displacement in other coordinates. Remember that. So when I'm working with first coordinate, I'll just give unit displacement in first coordinate. Okay, and I'll not give any displacement in other coordinates. So what is the force required for developing unit displacement in first coordinate? Like in this case, I gave unit rotation in first coordinate. So what is the moment required for developing unit rotation in first coordinate? If I find that, it will be coming over here. That value will be over here, K11. It will be K11 value. Okay. Then at the same time, with the unit displacement in first coordinate, if I find what is the force which is developed in second coordinate, so it will be here. That value, I'll put it over here. It will be the K12 value, which will be put over here. Okay. Similarly, next step is go for second coordinate. We are done with first coordinate here. Go to the second coordinate, give unit rotation in the second coordinate. Okay. So here the coordinate is corresponding to rotation, theta b. It is a rotation. So give unit rotation in the second coordinate and in the direction of coordinate. Okay. So when I give unit rotation in the second coordinate, what is the force required over here? Okay, that will be coming over here, K22. I'll put it over here. It is the value of K22. Okay, what is K21? What is the force in first coordinate? When unit rotation is given in second coordinate, it is nothing but it is equal to K12. If you have already determined K12, the same value will come over here. Okay, so this will be our stiffness matrix. Okay, so then these were the values of forces for unit rotation, for unit displacement in the coordinates. So if I want to know what forces are developed when theta A and theta B are applied in the coordinates, I just have to multiply this with theta A and theta B, this matrix. It is a matrix multiplication, please keep in mind. Okay, so this stiffness matrix will be multiplied by the displacement matrix. So that will tell me what are the forces developed due to the displacements theta A and theta B in the coordinates. Okay, due to the displacements theta A, theta B, what are the forces developed? Okay, so that is simply K into delta. K is my this stiffness matrix, delta is my this displacement matrix. That is what I have done here. Now, what coming to the next thing, what we are going to do is we are going to look into the equilibrium of the joints. Okay, equilibrium of the joints over here. So at joint A, okay, the net force Okay, the net force at joint A will be equal to force due to the displacements, which is P delta, force developed due to the displacements plus force due to the applied loads on the member. So it will be P delta plus P dash. Okay, if you add up these two, it will tell you what is the net force in the joint, in that joint A. Okay, so if at all, if there is no externally applied force at the joint, then normally this P will remain zero. The elements of this matrix will remain zero. So we'll identify that looking at the joints, whether there any forces applied at joint or no. Accordingly, the elements will be zero or they will be having some values. Okay, but this is the uh, equilibrium condition. This is how we are going to apply the condition of equilibrium. Net force in any coordinate will be equal to force due to the displacements plus force due to the applied force, P delta plus P dash. Okay. Further, what I can do, I can extend this as in the matrix form. So P is equal to P delta is K into delta. Stiffness multiplied by the displacement plus P dash will be calculated for the restraint structure, and I can go for rearranging entire matrix over here and go for determining what are my unknown displacements, theta A and theta B. Okay, so if you have theta A, theta B, if I give you the displacement values, you can use the slope deflection equation for finding MAB, MBA like that. Okay, that we will, that is a procedure what we will do it later. But here, one displacement matrix, P dash force matrix, okay, and the stiffness matrix, K, and one more matrix is the forces in the coordinate. What are the forces applied directly in the coordinate? Okay, these are the matrices what you should be developing here. Any doubt, difficulty or doubt, any confusion in these matrices, in forming or developing these matrices, what I said now? Anything you want me to repeat? You can unmute yourself and ask me to repeat that part. One more thing is the coordinates. Number of coordinates will depend on dk, the degree of freedom, and coordinates, where to assign these coordinates, wherever the displacements are taking place. Okay, like this, in this case, my rotations or unknown displacements were existing at joint A and B. It was a simply supported beam what I took over here. Okay, so the displacements were at joint A and B. So I have assigned two coordinates. Okay, the two coordinates are assigned at A and B. So I can go for choosing the direction of coordinate. Here what I have done is I've chosen the direction of coordinate as clockwise. Both coordinates are considered in clockwise direction. We have the freedom of choosing the direction of coordinates and numbering the coordinate. So at A I have given the coordinate number 1. Okay, at B the coordinate I have numbered it as 2. Okay, with reference to these coordinates and their direction we are working over here. Okay, we are developing the stiffness matrix in that form. We have arranged these displacements theta A, theta B, first coordinate, second coordinate, in this order only. Okay, similarly P1 dash will be the force in the first coordinate due to restrained structure. P2 dash will be force in the second coordinate due to the restrained structure, like that. Okay, is there anything, any difficulty in that part? Now I was talking about K11, K12. Okay, how do you get that K11, K12? You just leave this part, flexibility. When we are dealing with the flexibility, this one method, we'll come to this. Okay, at present, what I'm working with is the stiffness method. Okay, so I'll be only telling about this. So how do you come across this stiffness coefficients? How do you calculate those stiffness coefficients? Okay, so for this, you have these equations what I have here. Okay, so when you are worried about axial stiffness, okay, it is E by L. Okay, delta is equal to PL by E. Right now what we have is delta is equal to 1, so this will be, the force will be E by L. Okay, that is from that relation what we have, this equation. Now this transverse stiffness, okay, so you had this 12 EI by L cube. Okay, so when you have both ends fixed, okay, so if you want to find out the transverse displacement stiffness for transverse displacement, it is given by 12 EI by L cube. Similarly, you don't have to consider this. We'll not coming across this, because when developing the stiffness matrix, all the ends, other coordinates will be fixing the displacements. So if I want to know what is the stiffness coefficient for transverse displacement, it is given by 12 EI by L cube. Okay. Similarly, when it is a question of flexural or bending stiffness, okay, so 4 EI by L. Okay, you have already come across this 4 EI by L. If I want to have the bending stiffness coefficient over here, so if I want to apply unit rotation, say this is my one of the coordinate. So if I want to give unit rotation without any rotation at the far end, then the force here will be 4 EI by L. Okay. So if I substitute the properties of this member E, I and L, I'll be getting this value of stiffness coefficient. Okay. In the previous case, K11, I said, okay. In the second coordinate, no displacement was allowed. We wanted one unit displacement. Theta was 1. Okay. So in that case, K11 will be 4 EI by L. When I substitute the values of E, I, and L, I'll be getting the value of K11. Okay, this is how we get it. Now, at the same time, what is the force developed at the far end over here? It will be 2 EI by L over here. So K12 or K21 will be obtained by this expression 2 EI by L. Substitute the value of I and L for this member. We'll get what is this K12. Okay, like that we'll be calculating these stiffness coefficients. So these are the some common equations what we come across in stiffness method here. What we deal with is this transverse stiffness 12 EI by L cube. Okay, when I give unit translation, say when it is a case of a frame, okay, so it is a sway frame. So if I give unit translation over here, what is the force required for that? If I want to identify that, so this delta is 1 unit. So what is this force required? It will be 12 EI by L cube. 12 EI by L cube for this member plus 12 EI by L cube for this member. Okay, so it is given by this expression 12 EI by L cube. And bending or flexural stiffness is given by 4 EI by L. Okay, so this is how we calculate the stiffness coefficients by knowing these formulae. Okay, mainly we are dealing with transverse stiffness and the bending stiffness, these two equations. And in addition, what we require is 2 EI by L cube. Okay, so further, some more formulae we'll come across. We'll see that when we take the problems. Okay, when we have the problems, working with the problems. Please tell me anything else, any difficulty in this part. So this is the matrix method what we came across. We'll start with the problem in the next class. Okay, but this is all the procedure what we'll be following over here. We have to find out the matrices, apply the condition of equilibrium, and determine the unknown displacements. In short, this is what the procedure is there. You can put your USN for the attendance, those who were there earlier. If you have any difficulty, you can come and ask that. After giving the attendance, you can exit.